Fantastic. So at the top of the hour, so I guess we'll get started. So our first speaker will be Tslil Clingman. This is joint work with Fong and David Spivak, and they will be telling us about graphical regular logic, the complete two-dimensional picture. So Tslil, why don't you take it away?
All right, great. Can you hear me?
Yes, we can.
Perfect. So thank you very much for the introduction, and thank you so much to the organizers for allowing me to be here and talk about a project that I think is very exciting. And thank you, as I note, this is joint work with David Spivak, Fong, and a special thank you to both of those for including me on this project. It's been a good time. Okay. So just before we get started, a few words about me. So I'm currently doing my PhD in mathematics at Johns Hopkins University. I expect to graduate in 2022. I'm interested in formal category theory, higher categories, homotopy type theory, and computer implementations of these sorts of things, including general programming. If you'd like to find out more, please visit my website, tslil.xyz. And if you want to send comments, questions, or criticisms of this talk, please feel free to reach out to me at tslil@jhu.edu. I would love to chat about this. All right, so on to today's subject matter. What's the big picture? So this is the plan. We're going to start with some background on relations so that I can get to the main motivation of this talk, which is composition of relations. Then we're going to do a kind of depth first traversal of this tree. And each of the things marked with a warning sign, we're going to find somehow slightly or very unsatisfactory in trying to solve the problem we set out to do, and ultimately land up in the new work that I want to tell you about today. So without further ado, what's a relation? Maybe hyper-classically, the way that we want to think about relations is given a bunch of sets, say AI, a relation is going to be a subset of the product of these sets. So by way of an example, if we have the finite set of people and the lamentably infinite set of topics to study, one such relation on this pairing could be the relation relating people to topics that they've been exposed to. And so this relation includes you and the topic of, say, functors, because of earlier talks this week. So how do we compose relations? Because that's somehow the core of our interest in this matter. And what does it mean? So given relations R and S that we featured over here, note that R and S share a variable B. And so we may compose R and S to come up with a new relation on A times C. And the way we want to think about this is this relation, R composed S, is asking, is there a thing in the middle that via R relates A to that thing in the middle and via S relates C to that thing in the middle? By way of example, extending the tired joke that we had before, suppose in addition, we have a relation relating topics of study and talks at ACT 21. Composing these two relations lands us in something like those people who have exposure to a topic featured in an ACT 21 talk. And the thing that I want to point out is that we really are not very interested in which thing is in the middle, just that there is one that connects across all the way. That's maybe a very dry and uninteresting version of relation composition. So how do we start to attach this to real world things? Well, you know, very classically, we might write down some kind of giant set comprehension like this. And that's feasible in a certain select number of cases. But the point that I want to make is that we want to do things with relations that don't easily admit manipulations on the level of these kind of set comprehensions. And to see that, let's consider an example. The slogan that I want to communicate here is that knowledge is often represented relationally. So suppose that you're running an undergraduate chemistry lab, say, and you have a set of elements. I'm told the canonical ordering goes, there's antimony, arsenic, aluminum, selenium. And suppose you have a set of rooms in which we store some of these elements. Now, we might know certain things about elements in rooms. For instance, we might have a relation on elements which say which triples of elements react endothermically. We might also know where a given element is stored. We might store one element in multiple locations, and a location might store multiple elements. We might also know which elements are safe for undergraduates. And out of this knowledge, something that we might want to ask is, for instance, are there two elements which are the same such that when they react with a third element, it's endothermic. That third element is additionally safe for undergraduates, and we keep it somewhere. This seems like a reasonable question to ask of the knowledge we have so far. And the thing that I want to convey is that we can depict this kind of query on our knowledge in a graphical fashion. So considering this diagram over here, we have these two external wires representing the results of our query. Because they meet internally, we ask that they're equal. And then because we split this one wire into two, we duplicate that element. And so this is the, are there two elements which are the same such that part? Then we quantify existentially over a third element, and we split that element three ways. And we say, well, first of all, we want it to react endothermically with the two elements that we previously asked for. We also want it to satisfy the safe for undergraduates relation. And we also quantify over rooms, and we say there must exist a room, and we don't really care which one it is, so that we store that third element in that room. So that's an example of a graphical way to depict the sorts of queries that we're interested in making on relations. And ideally, this graphical representation would be kind of intuitive to handle. So for instance, this straight line over here would expect that this would be stable under topological deformations in some way. So whether I drew that as a straight line or a really wobbly line shouldn't matter too much. We'd also ask, for instance, that we could slide dots along lines and merge them. And that might be depicted by something like this over here. So saying first we existentially quantify and then we split it three ways is the same as just saying we existentially quantify into three places, as long as those are the same. We might also say things like, well, if two things are already the same, then it doesn't really matter in which order we use them. So we should be entitled to swap things around. And these are the kinds of stabilities and operations that we're looking for. But there are also other sorts of things that we expect a graphical calculus of relations to offer us. And some of these might be rendered as inequalities instead. So for instance, back in our lab situation, we asked for two elements which are the same, which react endothermically with the third element. Well, that should be included into any two elements, which are not necessarily the same. If we drop the restriction of equality, we should have a more general result. And so we expect things like taking this double-sided shape over here, that should be less than or include into just passing the wires through. We might also expect, for instance, that we've confined ourselves by restricting ourselves to only elements which are safe for undergraduates to handle. And so by deleting that and simply terminating a wire instead, we have yet a more general result. So these are the sorts of things, when I say intuitive graphical manipulations, that we would be looking for in a graphical calculus of relations. Unfortunately, the classical version of the story is very, very difficult to manipulate. This query that we've spoken through now would be rendered as some set comprehension that looks roughly like this. And I hope that you'll agree with me that it is much less intuitive and straightforward to manipulate a giant set comprehension than it is to rearrange some wires on a picture according to some laws. So this is our goal. And how do we achieve this? Well, the first thing that we need to ask ourselves is, what sorts of things do we need in order to study the calculus of relations? It turns out that the least we can get away with in a language is this fragment of logic called regular logic. And that's the fragment of logic that has existential quantification, equality, conjunction, and a true symbol. And we can see how these various symbols appear in our composition of relations down here. So we have an existential quantification, we asked the two elements were the same, and we took a bunch of conjunctions to make sure that all the relations held. All right, well, we're an applied category theory conference, so we should ask the category theorist, how do we study regular logic? And the category theorist might tell you, well, in a regular category. Now, I'm not going to tell you too much about what regular categories are, but suffice to say that they generalize some aspects of the category of sets. And this is the way that we want to think about it. So I mentioned before that a relation was a subset of a product. Now, in a regular category, the way we think about a relation is as an object with two morphisms to each component, such that those morphisms obey something called joint monotonicity, or in other words, the induced map into the product is in fact an inclusion. So that's the kind of anodyne generalization that we make for relations. How about for composition of relations? Well, I've rendered the old set theoretic comprehension story on the bottom left. And if we've seen these kinds of things before, set comprehension should say something like pullbacks to us. And indeed, that's morally what's going on when we compose relations in a regular category. Note the appropriate amount of quotation marks around this. It's not actually the pullback. If you know enough to know that, then great. But if you don't, it's pretty much we just have to do some kind of image factorization thing. Anyway, the idea being we take our relations R and S and we pull back over the thing that they share. And then we do something. Okay, great. So the category theorist has told us how to situate relations in a kind of general framework. But this isn't satisfactory. And this isn't satisfactory because of this reason. I mentioned earlier that a relation is now an object of a regular category. And that's really not how we think about relations. We think about relations as being things that live between objects. That's really what we want to say. A relation lives among objects. How do we do this? Well, the category theorist might answer, I know something that lives between objects. That's a morphism. And indeed, that's the approach of Carboni, Walters, and others. So their idea is to take a regular category R and formally construct a new kind of thing, which I'll call rel R, which features relations as morphisms between objects, and thus privileges them in the way that we'd like. This new kind of thing, it turns out to be a bicategory, which means it has objects, it has morphisms, and then it has two morphisms between the morphisms. So somehow we've gone up in a dimension. And what does rel R look like? Well, the construction goes something like the objects of rel R are once more the objects of R. So in the case of sets, the objects are once more sets. But now the HOM between A and B, we formally set to be the collection of relations on A and B. And these are jointly monexpands in the regular category R. To compose relations, or to compose morphisms in this bicategory, we have to do the underlying relation composition in the regular category R, which is why we don't really land up with something called a two category. There's some kind of bicategorical stuff going on here. And all of this works. But Carboni Walters observed that there are a few things that make this a very kind of special bicategory. And the first thing that I want to draw your attention to is the fact that it's not really a bicategory. If we look at these HOMs and we think about the category of sets, given two relations, either a relation is a subset of another or it's not. There aren't many ways to compare them. And so the observation is that this rel R, instead of being a bicategory, is something that we're going to call a po-category. And there are two ways to think about that. Either it's a bicategory, which is somehow thin in the highest dimension, or it's a category which is enriched over posets, whichever you prefer. So the HOMs are posets. So these two-dimensional morphisms are not very wild. Also, this bicategory is monoidal. A regular category has, among other things, a Cartesian monoidal structure, which the bicategory inherits. And then there's some other things going on. And Carboni and Walters initiated a very successful project in trying to axiomatize those other things. And they were successful in proving that kind of symmetric monoidal Po categories plus, other things are exactly the regular categories. So they managed to take regular categories, privilege the relations, view them as morphisms, and not lose any information in doing so. And that's really great. And that's a nice project, but it fails the kind of central thing that we were aiming for. There are no pictures in this story. So how do we put them in? Well, this is where this project picks up with Fong Spivak. And they said, well, let's take a look at this picture over here. This is the thing we want to draw. So let's forget about the details of what's going on. Let's forget about the names of these relations and what the wires are called, and just look at the wiring for a moment. And they observed that things that we can do to wires include, for instance, start a wire out of nowhere, and that appears over here. We can split a wire into 3. We can split a wire into 2. We can merge 2 wires. And then we're allowed to glue these kind of constructions onto one another to obtain more complicated shapes of wiring. And they decided to axiomatize what it means to have wires that obey these sorts of laws. And they came up with this idea of the Po-prop for wiring. And we're going to call that thing W. So I'm not going to say what a Po-prop is. I think that's maybe not the point. But I'll tell you how we should think of W. So it's a symmetric monoidal Po category, and it's generated by pictures that look like these, and they have names. These things are morphisms, and what we should think about them as being is the kind of abstract calculus of things like variable duplication or equality of variables or existential quantification and things like this. So we have these generating things, and they should be subject to certain relations. And we've seen some of these before. For instance, if we split a y in 2 and then swap the 2 ends over, well, this is somehow variable duplication, so it doesn't really matter. That should just be the same as not having swapped the 2 y's over, right? And many other laws, as well as some inequalities. And one of those we saw earlier again, which was constraining a variable to be 2 variables to be equal and then duplicating them. That should be less general than just not constraining things in the first place. And now there's some fancy words for what this gives us. It's some kind of special commutative Frobenius monoid and the whole story. But the summary is that there's an algebraic structure which says exactly the sorts of things that should be true of connecting relations, not relations themselves, just the ways in which we connect them. So Fong and Spivak went on, and after isolating this algebraic structure, after isolating this algebraic structure, they described what it means to supply wiring diagrams. A supply of wiring diagrams in a symmetric monoidal Po category C is essentially a way to draw string or wiring diagrams for the morphisms of C, where the wiring is controlled by W. What does that mean? So that means if C is our symmetric monoidal Po category over here, say R is a morphism from A to B, and T is a morphism from B to C tensor C, then we're entitled to take this morphism and glue on a wire, say E to A, and more wires, such that the wiring component obeys the exact laws that W sets out, and the morphism composition all happens in C. In other words, they described a way to describe complicated composites of things that should behave like relations in a symmetric monoidal category. And I want to say that the kind of technological advantage of this over regular categories is significant. For instance, I've sketched out here the sort of thing that would have to do in a regular category if we wanted to describe the same sort of composite. And that looks like taking a huge amount of pullbacks over many, many things, and then doing some image factorizations and some isomorphisms before we can finally conclude that we have something that lives over C tensor C as depicted over here. So this is great. And the this is great part, I mean specifically the following theorem. Fong and Spivak proved that there is an equivalence or an isomorphism between regular categories and symmetric monoidal categories which supply W and some terms and conditions. What this really means is that a category behaves like objects and relations between the objects precisely when we can draw wiring diagrams between them. And that's the thing that I really want to highlight in the genesis of this project. We agreed that regular categories are the correct place to talk about relations, but they didn't expose the graphical nature. And Fong and Spivak showed us that, in fact, there is a graphical nature, and we can reason about these things in a graphical way, exactly as though they were regular categories. And I think that that's a very nice theorem. But it's still not satisfactory. And it's still not satisfactory for maybe a subtle reason. It turns out that the underlying technology of Fong and Spivak and other similar approaches depends on a symmetric monoidal category. Okay, what that means in particular is that relations are viewed as morphisms, and morphisms have a domain and a codomain. Well, that's kind of alarm bells. We're privileging binary relations by asking for relations to be morphisms in this sense. And what I mean by that is, suppose we have a relation on A, B, and C. In order to make it fit into this picture and similar pictures, we have to pick whether the domain of R is A, or say A tensor B, or A tensor B tensor C, or any of the other various permutations and combinations that we can come up with. We have to make a choice. And my claim is that it is unnatural to decide one way or another in which HOM R should live. And that is a problem that is present in all of these frameworks so far. And that brings us to the new work that I want to tell you about today. So how do we resolve this? And the idea is we come up with a new place which is supposed to house regular theories in some very comfortable way. And we call this new thing a regular calculus. And a regular calculus is essentially three things. It is, first of all, a symmetric monoidal category. But this is not where the relations live. Instead, the objects of the symmetric monoidal category are things that I'm going to call contexts. And because it's a symmetric monoidal category, for instance, if A and B are contexts, then so is A tensor B. The morphisms of the symmetric monoidal category are things like context maps. They tell us things like, we duplicated a variable from this context to arrive at this other context, or we existentially quantified, and so on and so forth. So the context maps, again, are not the relations in this picture. They're just things that tell us how to abstractly turn one context into another context, subject to kind of this regular logic. And the subject to part of that comes from the supply of W. So we ask for a regular calculus to have a supply of the wiring prop in its symmetric monoidal category of contexts. This gives us two things. This, first of all, allows us to draw pictures of context morphisms. But second of all, it allows us to say that there are certain structured context maps like the ones that I suggested earlier, the ones that existentially quantify or duplicate variables or ensure that two variables are equal. And the last thing that we ask for in a regular calculus is a so-called Ajax pofunctor. And this is the added data of the relations. So this is not part of the symmetric monodal Po category. It's not part of the supply. This is something that we ask for on top of everything else. I'm also going to switch terminology now. Hopefully it won't be too confusing, but I want to emphasize the kind of regular logic aspect of things. So instead of calling things relations, I'm now going to call them predicates. And these things are really in bijection. So where a relation is a subset of the product, A times B, a predicate is a formula in the variables drawn from A and B. And there's a way to go back and forth. So given a relation R, we can come up with a predicate on variables in A and B. And that predicate says 5AB is true precisely when A and B are related. Conversely, given a formula in variables AB, we can come up with a relation on A times B. And that relation is all those pairs AB such that 5AB. And we can check that this is a bijection. And so under this thing, instead of considering R to be a relation on A times B, I want to consider phi to be a predicate in P of A tends to B. And this is the added data of relations. So that's the definition. Let's take a look at an example, or should I say a large class of examples. Given any regular category R, say for instance, the category of sets, we can construct a regular calculus, which we call the regular calculus of predicates in R. In order to construct a regular calculus, recall we need three things. We need, first of all, a symmetric monodal Po category for our category of context and context maps. And for this thing, we take, and a little bit confusingly, we take the symmetric monodal Po category of relations in the regular category. We also need a supply of W wiring diagrams in this thing. Well, fortunately, the theorem of Fong and Spivak that I mentioned earlier gives us exactly such a tool. And finally, we need an Ajax pofunctor. This is the a priori added data of relations that were not previously, or predicates that were not previously part of the picture. It turns out that in this case, because R, the regular category, is in fact Cartesian monodal, we can get away with taking a representable functor. But in general, one should think of this as being added data and somehow not part of the category of contexts. Anyway, we can build this gadget. And what does the regular calculus of predicates look like? Well, it has contexts, which are the objects of the regular category. And if we go through all the calculations, it turns out that predicates in a given context, gamma, are precisely the sub-objects of gamma. And this is exactly what we wanted from this story. For instance, if gamma was the set A times B times C, then it turns out that the predicates in the context gamma are exactly the relations on A, B, and C. And we have completely done away with any kind of binary privileging here. We're not asking for there to be a domain or a codomain or anything like that. And we can go through and check all these calculations. And in summary, we find out that existential quantification, conjunction of predicates, equality, true, all of these things come out exactly to be the ones dictated by the regular category R. And that's very, very nice. So what we've done so far is to find a new structure, a regular calculus. We've found a way to take regular categories and turn them into these things, talk about relations or predicates in a regular category without privileging any kind of binary notion of composition or binary notion of definition. But where are the pictures? The central goal of this talk was to have pictures for relations and operations thereupon. Well, it turns out that a regular calculus in particular asks for a supply of the wiring Po-prop in C. And we know that supplies of this wiring thing allow us to draw pictures. And so we can define something called a graphical term in irregular calculus. A graphical term in irregular calculus is a wiring diagram in the category of contexts where the internal wires are annotated by predicates, which are drawn from this Ajax functor P. So for example, this thing, which was our stated goal, is in fact a graphical term. We've drawn R from P of A tensor B. We've drawn S from P of B, and we've drawn T from P of B tensor C tensor C. And we didn't have to worry about domains and codomains or anything. And we've wired them up with morphisms or wires in the symmetric monoidal category of contexts. And this whole thing represents a new predicate in P of C tensor C. And this is really, really nice. And because of these kind of supply of W and various other theorems that we prove along the way, this affords us the sort of intuitive graphical manipulations for a calculus of compositions of relations that we wanted in the first place. But so far, everything I've said has been an island. How does this compare to regular categories? Well, we prove, first of all, that this turning a regular category into a regular calculus is a two-functor. And so it's a very good assignment somehow. And more than being any two-functor, we in fact managed to prove that this assignment of regular categories to regular calculi has a so-called left bi-adjoint. So this is some higher dimensional version of an adjunction. I'd be happy to talk this specifics at the end of the talk. And this left bi-adjoint we call the syntactic Poe category construction. So this is maybe reminiscent of other scenarios in which we have a kind of syntax semantics adjunction. And the idea here is that regular categories are somehow the syntax and the semantics of these regular calculi. And the nice thing about this left bi-adjoint is that it is given on objects by taking graphical terms. That is, we send a regular calculus to the regular category whose objects are graphical terms in that regular calculus. But better still, we managed to prove that the co-unit of this bi-adjunction is itself an adjoint equivalence. And what that amounts to is saying that taking predicates from regular categories into regular calculi is some kind of two-dimensional embedding. And so the thought that I want to leave you with is that this means that we can work graphically in a regular category, which is not something we asked for right at the beginning, but it is something that comes out of this theorem. Why is that? Well, recall that I said that the co-unit is some kind of adjoint equivalence. And that means that if we start with a regular category R and we do this round trip, we land up with an equivalence of regular categories. But the thing on the left has objects, which are these graphical terms, and so has a graphical calculus to manipulate and perform calculations in it. The thing on the right is a regular category, and so putting these two things together, we actually land up with a graphical calculus for regular categories. And that's it. Thank you very much. Here are some references. Please be on the lookout for our forthcoming papers on this topic. And thanks so much for your attention.
Great, thanks, Will. Great, so we have a few minutes for questions. Does anyone have a question that they'd like to bring up? You can unmute yourself, you can throw it in the chat.
There's a question from Jamie.
Okay. Hi, Tslil. Thanks for your talk. You know that I'm super interested in this work that you and Brendan and David have been doing. We've chatted about this before. So do you mind if I ask you the same question I asked you last time? Because it was a while ago that we talked about this last time, right? And because I mean you, I mean with the end of your talk, right? You make what for me is a really exciting statement that this gives a graphical calculus for regular categories, which, as you say, isn't something that you described the motivation of the project very nicely. That's not something you went in to as a goal, but something that comes out. So regular categories have got finite limits. So they've got finite products and they've got finite equalizers. So can you sketch for me an example of how you would use this graphical calculus to construct the equalizer of a pair of morphisms graphically? And then you take the co-product of those, and sorry, not the co-product, the product. And I want to see how to work graphically, not only with the compositional structure in the regular category, but also with the finitely complete structure.
Sure. Thank you for that question. I think that's a really reasonable request. I think in the heat of the moment, I'm not sure what I can do, but I'm certainly willing to try. But this sort of, for instance, picking pullbacks or something depends on some kind of other sensitive bit of information that we have to show happens in here. And this is something called tabulators. We need to be able to construct tabulators for morphisms, which it turns out we can do. They have kind of nice pictures. And that's what kind of lets us work towards the finite limit structure a little bit. I think you'll be quite underwhelmed by the picture, unfortunately. So it turns out that if we want to describe a tabulator of a morphism like this, which is a factorization as a left adjoint followed by a right adjoint given some universal property, it turns out that the tabulator looks a little bit like that, and I can't immediately remember which is the left adjoint and which is the right adjoint. But that's kind of the start of things. So these tabulators are the things that allow us to construct pullbacks of left adjoints and things like that. And this is where the limit structure starts. But it looks a lot like the rest of the wiring diagram somehow. I'd be happy to think more carefully about this and give you a better answer if that's okay.
Yeah, I wouldn't say I'm underwhelmed. I would say I'm neutrally whelmed currently. And I look forward in the future to being overwhelmed. Okay, thanks for your answer.
Sure.
I think we have time for another quick question if anyone has one.
There's some online as
well. Okay, yeah, well, there's one more question in the lecture theatre, but there's also one online, so it's up to the chair.
Oh, let's go online.
Is that me?
Sure, yes. I believe
Great.
so.
So my question is, there's also another way to work, there's another graphical calculus to work in a regular category. It's the sort of Cartesian bicategory of relations string diagrams that I'm sure you're aware of. They're very similar. I'm wondering if this graphical calculus buys us anything structurally, like maybe can we represent joins of relations with some extension to it, or something that we couldn't do in what I think of as the usual graphical calculus. I also had a question about tabulators, but you just answered it.
So I mean, the technical advantage. So I mean, the answer is maybe at first no, and that is because the thing that this is correcting is somehow the underlying encoding, and the string diagrams are already oblivious to that underlying encoding. I spent some time complaining about how relations need domains and codomains, but that's not present in the string diagram calculus. So at that level, no, but also yes, for a different reason, which is that I said that this is only the co-unit is an adjoint equivalence. So there are regular calculi which are not somehow regular categories. And so in some ways, this allows us to reason about other things.
I think this is, I mean, in the same way, right? If you don't have tabulation for a Cartesian bicategory of relations, there are also those
Sure.
that don't correspond to regular categories. I'd be surprised if it wasn't the same thing is what I'm trying to say. And I'm wondering if your notation lets you represent something new.
So more than not just having tabulations, there are also these things, that say that we want certain inequalities between pictures that look like this.
Yeah.
And regular calculi don't have that either.
Okay.
Which I think Cartesian bicategories do, even if they don't have tabulations. I'm not very sure about that.
It's okay. Maybe we can talk about it after.
All right.
Thanks.
So Pawel, is your question very quick?
Yeah, I mean, actually, most of my questions have already been asked, but maybe just one. Can you tell me a little bit about how you define the graphical terms? Because on the one hand, you were saying that you define them out of these these basic wiring algebras together with the relation symbols, which are predicates. But then your pictures, they don't really look like that. There's some vertical wires. So like, what's the go-to definition of what does that picture actually mean?
Right. Yeah, I took some liberties, and you're absolutely right to call me out on this to make it look a little bit nicer. The kind of somehow rigorous definition would be we start with a wiring diagram in the symmetric monodal Po category. And we start off with a bunch of predicates in each one of these things. And then a graphical term is using various bits of structure. Sorry, this should be first to the external product. Using bits of these, sorry, that's the wrong thing. P is an Ajax pofunctor, and so we can do this sort of thing, and that's what I mean by a graphical term. So we pick some diagram in C, we pick some predicates in each of the P's over the things, and then we use the kind of lax monoidality of P to put them all inside, and then we act on it with the wiring diagram. And I've kind of abused the fact that we can, topologically deform these pictures so that some wires are vertical and some wires are horizontal, but maybe more strictly pleasingly, this picture might have looked like, and so on. I'm not confident I can do this on the fly, but something proceeding entirely horizontally.
Okay, thanks.
Great. So can we have another round of applause for our speaker, Tslil? And maybe we can move on to our next speaker, would be Guillaume Boisseau, who I believe is in person.
This is the visible zone. Can people hear me?
Yes, we can.
How does this work?
Okay, are you ready for an introduction?
Yeah, I can't move the slides. Yep.
Great. Are you ready?
I am ready.
Fantastic. So let me introduce our next speaker, Guillaume Boisseau. His co-author is Pawel Sobociński, and he'll be speaking about practical diagrammatic electrical circuit theory. So why don't you take it away, Guillaume?
Thank you. Hello, everyone. Thank you for having me here. Today, I'm going to talk about analyzing electrical circuits using string diagrams, and this is a joint work with Pawel. I'm trying to do a very non-technical talk, so there should be a light on you. So a bit of context first. We already know in applied category theory how to analyze electrical circuits using string diagrams, and I'll explain everything in a bit. But it's been shown very nicely in a few different ways. But I want to take it a bit further in the applied direction and ask whether this is actually a practical endeavor. Like we know we can do it, but can we do it for real? Can I write a textbook using only diagrams? Can I forget completely about the underlying linear algebra? And my answer is yes. I actually tried this, and I'm going to show a few things in that direction today. Okay, so the context is graphical linear algebra, which the basic idea is very simple, is instead of writing equations using normal equations and mathematical terms, we draw diagrams. And here on the left, you can see a diagram that has a few different building blocks. And the way you read it is each wire is a variable, and the different blocks do different things. So the black dot does copying. And so we see A is getting copied and then multiplied by 2, and that gives C. That's the first equation. And then the white dot does addition. So A gets copied, multiplied by 3 plus B gives D, right? So any equation, any affine equation specifically can be written like that. So these are the basic building blocks. We have the copying, we have the addition, we have a constant 0, constant 1, and multiplication by k. And using those, it's not too hard to convince yourself that you can write any set of affine equations. And so composition works as you'd expect. So when we plug two variables together, we identify them. And don't look too much at that. I'm just showing it. Those are the axioms we use to reason about this diagram. So obviously we want to know when two diagrams, represent identical or equivalent sets of equations. And the reason GLA, graphical linear algebra, is very interesting is because we have a complete set of axioms. So we have a set of axioms that are purely graphical that allows us to derive any equivalence. So if two diagrams mean the same equation, then we can prove it graphically. So at least in theory, we should be able to completely forget about the underlying equation. We should be able to completely forget there is linear algebra underneath and do everything in this at the level of pictures. And this is what I tried with electrical circuits. So here is how it would work. So electrical circuits, I'm guessing most of you have seen this in high school or something similar. The idea is that we have basic physical components that we will actually physically wire together, and we model them using a little diagram. So every element, every physical component, we have an element, and we're interested in two physical variables, the current and the voltage. And every element will have a small equation, small linear or affine equation that describes its behavior. And so here we can have the basic one is the resistor. So we have a resistor of resistance R. And I notate the currents and voltages at each port of my resistor. And this is the equation it gives us. It's Ohm's law. It gives us that the voltage difference is proportional to the current. And that the input current and output current are the same. Note that I'm writing currents going to the right, which might be unintuitive, but it makes prettier pictures. And if I write this graphically, I get the nice little diagram on the right. And you notice that I've chosen to write on the top wire the voltages, and on the bottom wires the currents. And I can do that for all the basic components. So I have resistors, inductors, capacitors on the left, and then voltage and current sources on the right. So voltage source imposes a particular voltage difference, for example, and the corresponding equation. And finally, the last bit we need is the actual wires themselves. So we have the sort of identity wires that does the identity. And we can join wires together, and then they obey, again, electrical laws that we know. So the potential is shared and the currents sum to 0. And now using those, I can write any old electrical circuit. And the interesting part, and the very nice part, so far this is well known, I haven't done anything new, is that this is compositional. So if I take a circuit, electrical circuit, I break it up into its individual components, and write the equation for every single component, and then plug them back together in the same shape, then I get an equation that describes the behavior of the complete circuit. And this tells me that the diagrams have got something quite nice. They highlight some of the structure we know, some of the topology we know from the circuit. But in the diagram is a big for a small circuit. So is this actually practical? Well, let's try to prove something, right? Here is a very simple equivalence between two circuits. So we plug two resistors in series. And in a few steps, the first step, I write the equations for each element and plug them together. And the second step is associativity of the black and the white dots. Third step is distributivity. So all those are axioms of linear algebra. And the final step is noticing that this exactly is describing a resistor, as I showed last slide. So now we have shown that those two circuits are described by the same equation. So that's what we mean by equivalent. They have the exact same behavior. And we've proven a very simple, like actually physical, electrically true thing. That's pretty nice. And I claim that we can do essentially all of those practically. But first, I need to introduce two sort of notational innovations that makes this kind of work. And the first one is noticing a pattern here, that you may notice that all the elements kind of have the same shape. They all have a white dot on the voltage wire and a black dot on the current wire, which reflects some underlying truth of the physics. But what it also means is that I can introduce notation for this particular shape. And I will write a little diagram inside a blue box. I will call that an impedance box. And that will describe the diagram on the right. And the reason I'm doing this is because you might notice that the equation, like the equality 2 on top, doesn't care. I could replace R1 and R2 by any old diagram, and that will still hold. And what this gives me is a general equation for what happens when I put two of those boxes in series. And I also have, and that would take a few more steps, a general equation for what happens when I put two of those boxes in parallel. For resistors, it gives us what we know. So resistors in series sum, and resistors in parallel get the inverse sum. But that also works for all the other elements. And that's really cute, because that means for many circuits, many simple circuits, I can just reduce in parallel and series any elements and get in a few steps an equation for general circuit. And this generalizes something that actual engineers do already normally, which is called complex impedance, which already says, well, let's pretend that capacitors and inductors behave like resistors. And I mean, there's a formal thing underlying this, but they can do this for those three components. And we can go a bit further. We can do it for sources as well, and it's quite general. So this is the first step that makes solving circuits practical graphically. And you can do a few. You can pick an example from a textbook and try to do it that way. It works out decently if you're familiar enough with the graphical linear algebra. But then we have a second problem, and the problem is closed circuit. So take a closed circuit, which is a circuit that has no open wires, and try to write the equations for it. The problem is that the way we defined everything, the corresponding equation has no open wire either, which means it has no variable. It's an equation with no variable, which is obviously extremely boring. There's only two such equations. There's the true equation, the false equation. So in that sense, we've lost all the information about the circuit we cared about. And the idea is that I wanted to know this current I. What is this current I? It doesn't really exist in this picture, but it kind of does. If only I could tap into that wire here, just copy it out, then I would get the current I'm interested in. And how can I do that? Can I make sense of this at the level of vector circuits? Yes, and this is again showcasing that diagrams are quite convenient. I can just add things and they work out. So let's pretend I can do this, and it turns out you can make this formal. But let's pretend I can mix wires. So now on the electrical side, I've got the electrical wires as before that are blue, and I add new wires which are black, which I will call information wires, and they will carry the results from my measurements. And if I write this on the left, so here's the little A is an ammeter, which is an actual, the name of the actual electrical device that measures current. And it will output the current and a black wire. And now I can actually observe my closed circuit, get the corresponding equation, solve it, and get that the current here is V over R, or maybe minus V over R. I wasn't careful with the signs. And so I introduce this. So I introduce it using impedance boxes. So it's literally just taking the current and sort of putting it out the box. This works exactly as you'd expect. We also have voltmeters to measure voltage difference. And for symmetry, we can also do this for sources. Instead of having a source that gives us a fixed voltage, I can ask it to read off the voltage from an input information wire. And now we have the two tools that make this whole calculus practical. Now I can actually prove real theorems of electrical circuit theory. And I'm going to show two of those right now. Okay. first theorem is the theorem you might know. Current is conserved in a circuit. So if I take a circuit C and I measure all the currents going into the circuit, those currents should sum to 0. That's what a very general property of circuits that reflects underlying physics. So the first question is, can I write this fact using diagrams? So let's take a circuit C. Let's measure the currents going in and out. Let's sum all of these and then sum the input and outputs together. And this equation, the equation I'd like to be true, says that, well, exactly what I want. If I sum all those currents, then they give 0. And the rest of what happens on the electrical wires is just the behavior of the circuit itself. It shouldn't interfere in any way. Can I prove this? Yes, and in fact, it's quite a reasonably simple proof by induction, right? So I prove it for all the basic elements. So here, the example is take an impedance box with some X. Then in a few steps, using what we saw previously, we can prove that, yeah, that holds. And then we have the inductive case. When I plug two circuits together, does it still hold? And again, it takes a few steps to justify, and it holds. So here we see, I like this example because it shows that it shows something nice like the diagrams. You see what, yeah.
Could you clarify what's happening in the second equality, please?
The second equality of the inductive case.
Just in the middle, yeah.
Yeah, no. I mean, yes, but it's an instance of the theorem we want to prove for the single wire. So you have single wire plus 0 is the same as having two ammeters connected with a white dot. And then you manipulate the white dots in some way. But yeah, so it works out. And it works out in a way that you see what's happening, which I quite like. That's a general property of diagrams. You tend to see what's happening while you're doing it. You're not too confused about what the next step is. Anyway, so that's the first theorem, the first actual real theorem we can do. And depending on how much time I have, I can do the second theorem, which is a very useful and actually used all the time theorem that engineers use all the time. It's called the superposition theorem. And what it says essentially is that the behavior of a circuit is linear in its sources. And that's why it's very useful, because when there's many sources, you can take them one at a time, solve for whatever you need, and then sum the results together. And that gives you the whole overall behavior of the circuit. So engineers use it all the time because that makes everything much simpler. And this is what it looks like in a picture. So for a simple example, I have my circuit C that has two sources, and I'm measuring one current somewhere in the circuit. And I claim, and the engineering textbook would claim that there's equality between those two things, right? So on the right, I'm turning the source, each source one at a time, and then summing with the white dot the behaviors. And this is somewhere else that the diagrams, I mean, not only expressed, I like this picture that is quite legible once you know what's happening, but also it forced me, notice that I don't have an equality here, I have an inclusion. And the reason is that the engineer is completely justified, but the engineer would ignore a bunch of circuits that they call degenerate because they don't correspond to something physical. Usually because there's some kind of short circuit somewhere, it makes it some impossible solution or many solutions. But I want to be faithful to the math. And the diagrams force me to be faithful and to notice that it's not an equality. I can show a counter example if you want, that this is an actual true equality. But I do have the inclusion, and the inclusion is usually mostly enough for what we want to do. And this is yet again, the way to prove this is, it's actually, if you know enough graphical algebra, this is almost trivial because it's a theorem you use all the time anyway. Otherwise, it's a nice proof by induction if you want to do it. Once again, I completely can prove this without much hassle, purely diagrammatically. So those my two examples of actual real theorem. So the takeaway that I want you to get is that this is credible. This is a credible alternative. I actually went through, so I took an engineering textbook on electrical circuit theory. I went through the theorems and proofs and examples, and I tried to reprove them, and it turns out that all of them are doable. Most of them work out pretty nicely. Some of them are a bit more involved a few tricks. But the proofs tend to be very elegant, very general. Like I was surprised how nicely it worked out. So this is a credible alternative. I kind of want to see a real textbook with that in it, in some sense. And it shows a few good things and a few bad things about diagrams. So they're quite good at obviously inductive and topological reasoning. They're extensible. I liked how I could just add things and figure out if they made sense afterwards. And in this case, and this is a place where graphical linear algebra particularly shines, it is naturally relational. And circuits also are relational, even though the engineer would tend to say, let's assume there's a matrix that describes anything. And that's not mathematically correct. And diagrams don't care. They make this very nice. They're just like, yeah, I don't care. It's relational. I can describe it very faithfully. So conclusion, this was a ton of fun. I generally find this very enjoyable to go through this textbook. I want to see more of that. If anyone wants to play with those and do some already done math in a new way, I recommend it. Thank you.
Thank you, Guillaume. So we have some time for questions. So any takers out there? I see someone.
Yep.
Andrew Pitts.
Yes, hi. Do you think, would this approach extend to scary world of memristas?
Of memristas?
Yeah.
I've never heard this word before. What are those?
Oh, well, let me quote. A memristor is a nonlinear two-terminal electric component relating electric charge and magnetic flux linkage. It was predicted theoretically in about the 70s, but now they physically exist, and they're an exciting thing. But it would take you beyond linear algebra. I just wondered whether you thought about it.
Would. So what's interesting is that like a lot of what I do doesn't really rely on it being linear algebra. I'm mostly using what was just shown in the previous talk. We have a graphical calculus to talk about relations. And in the case where I have linear algebra, there are a lot more theorems I can prove because everything is linear. It's still manageable and useful without the linear. You still get the compositionality. You just don't, you lose a lot of the inductive properties, you lose it because you can't describe all of them, all the relations anymore. But you can get some nonlinear stuff. We do have diodes, for example, not in this in this thing, but we can extend it to diodes, adding a few things to the underlying language, and it still works out. You can still reason about circuits. So it would be a bit less nice, but still keep good properties, I think.
A question from the lecture.
Thanks, Guillaume. Really great talk. Just out of curiosity, could you comment on how this relates to Lagrangian relations that we've seen before?
We've been discussing it with Cole quite a bit. So most of the basic elements, so all the basic elements I've shown are Lagrangian. So in some, there's overlap, but it's kind of different angles on the thing. Like the theorems that you would get from Lagrangian relations, yeah, I have them, but I also have some elements that are not Lagrangian. So it's not like it's somewhere there. I'm not exactly sure how useful it is for me in this particular setting. But I've encountered the same properties, and like Cole was quite interested in that. I don't know. It feels like an accident that gives me a few nice theorems rather than something fundamental to what I'm doing in this case.
Thanks.
So I see another question in virtual land, Matt Insall.
Yes, thank you. So I saw that you implemented measurement devices. Have you also implemented measurement error and error analysis in this setting, or thought about it at all?
I have not thought about it at all, no. But I'm assuming it wouldn't be as linear anymore. So probably it's the same answer I gave earlier, is once we go out of linear, then we can prove a lot fewer theorems. But yeah, that's an interesting
You can use linear algebra in that context because inner product spaces give you a notion of distance. So, okay. Yeah. And distance is used for measurement error and error analysis.
I never thought about it. That sounds interesting because it sounds also quite compositional.
Right.
Yeah, thank you. I'll look into it.
Okay, why don't we call that the end of the presentation. So let's thank our speaker again, Guillaume. Thank you. And I guess we'll get set up for our next speaker. Okay.
See the slide?
Yes, we can see your slides and I can hear you. So are you ready to go?
Yep.
Fantastic. All right. So our final speaker for this section will be Alberto Speranzon, and his co-authors Brendan Fong and David Spivak, and he'll be telling us about temporal landscapes, the graphical logic of behavior. So Alberto, why don't you take it away?
Thank you. So let's get, let me see here. Yep. So I'll start a little bit with the motivation of this work. So this really is, insert itself within this idea of modeling and analyzing complex system of system, and more specifically, really on the analysis of complex system of systems. So David and I and Patrick and Brendan, we were involved in a project with NASA in understanding how to model and analyze complex system of system. And the starting point there was to rethink about what signals and systems really are. And probably many are familiar with the work that has been done in this area, thinking about signals as shifts over time intervals, thinking about systems as this notion of abstract machines, and then be able to exploit the compositionality of this to analyze complex systems. So this is, sort of very different than how typically people think about this system in engineering, but obviously brings a very nice framework to analyze complex system of systems. So from a modeling perspective, we can model complex behaviors, thinking about this, as I mentioned, the sheaves and use of abstract machines and compose them to describe the full system. However, if you want to do analysis of this, things it can be done, but things are complicated. So the question there was, how do we analyze the behavior in a way that is obviously mathematically sound, but is also easy and intuitive for a non-expert. Certainly, I come from industry, while I certainly like to be able to manipulate these objects like sheaves and abstract machines. Ultimately, if you want to make this usable in industry, you somehow would like to put under the hood all that technology and expose to the user something that is much easier and intuitive to be used. So while the mathematical framework is based on topos theory, this sort of easy and intuitive way of representing or analyzing and thinking about the behavioral complex system is what this talk is about, which is what we call temporal landscapes. So this gives you sort of the idea where this temporal landscape really sit themselves in, and why we were interested to look into this. So the temporal landscape really then provide the true value of a logical system that we call the temporal landscape logic. Formally, a temporal landscape on the real is just a set of time intervals, which have two key properties, the down closure and the openness. And so without getting to the formulas, just a simple picture tells us what this means. So temporal landscape will be drawn as a diagonal line representing time. So usually time is horizontal, but landscapes, we will draw time in a diagonal fashion. And really a temporal landscape tells us the truth value over time intervals. So in specific, if we draw these sort of triangles to simplify the fact that if something is true in the interval T1 to T2, is also true for any interval within T1 and T2. So this is the down closure. And if an assertion is true here, then it's also true for a larger interval. So the landscapes really are open sets, but in the next few slides, just for simplicity, we tend to draw them as if they look to be closed, but remember that they are not. Now the temporal landscape name comes a little bit because they resemble persistence landscape that I use in topological data analysis. If you're familiar with that, you may recognize some of this to potentially be confused if you squint enough. And another thing that we will use, we'll write prop to really capture the set of temporal landscapes. So with this defined, then obviously the question is, what can we do with this? Before we go into that, just a small nomenclature. We will call a roof over an interval AB the temporal landscape through between AB, which is nothing else than this triangle that you already saw before. So meaning that this predicate is true within AB and every interval under smaller than AB. So that's going to be sort of building blocks for the many things that we do. Of course, you wonder what true and false may be. Well, true is just the infinite roof in some sense. So a roof requires us that for any length of the interval, the predicate is true. So this is an infinite sized roof. And for false, we have that no interval is true. So it's just the flat triangle on the timeline. So this sort of simple enough. And if you consider conjunction at disjunction that between two landscapes, these are easy to be built as the intersection or the union of the two landscapes. And if you have two temporal landscapes and you are interested to draw the temporal landscapes corresponding to the implication, it's a little bit more subtle. It's going to be the intersection between the roof between AB with the temporal landscape for phi, whenever it is a subset of the temporal landscape C. So as a starting point to understand this better, we can take the negation, just being the implication to false. So this is going to be just the intersection being empty, which then recovered exactly what you would expect. So if you take a landscape phi and take its negation, we are going to draw a roof whenever the landscape is false. So here we have an example where phi is this temporal landscape, and whenever it is false, we have a roof. And so this is the negation of phi. You see here that we draw this temporal landscape not just to be a roof, but having sort of a curvy appearance. And so this is, more general. The temporal landscape do not need to be just this sort of orthogonal or square triangles. And we'll see at the end of the talk an example where in practice, this sort of curvy temporal landscapes actually are appearing as explaining some behaviors. And so we'll get into that. But this is pretty obvious what the negation does. So then if we go back to the more general implication and we look at what visually this is in the context of temporal landscape, then we have that we are going to draw a roof whenever there is the phi is contained in psi, otherwise it's going to be psi. So you can see that between 0 and 9, the temporal landscape of phi intersected with the true or the roof between 0 and 9 is always contained within psi, but between 9 and 15, that's not the case. So then the temporal landscape takes the shape of psi. And so this is the temporal landscape that comes out of the implication. And in the paper, we sort of discuss a little bit more about an example where this shows up more from an application perspective. So one thing that is interesting about this is that we can start using, so my interest coming more from the application was, what can we do with this? type of temporal logic and the temporal landscape as a sort of graphical way to discuss about behaviors. And so we were looking at, the simplest thing that you can think about is, agent system living in a grid. The grid, for example, is, typically just a graph. But thinking this more in the context of temporal landscape, really the vertices are just a constant behavior type, and the edges of my grid are a subtype of the vertex types, and it consists just a pair of vertices. So here, just to remind, when we say behavior type, really we are really thinking underneath about the sheaves over time interval, in this case being constant, just a constant sheaf over the interval. So it's sort of just a change of nomenclature, if you will, from someone that maybe doesn't know sheaves or doesn't want to remember that there are sheaves underneath. That's all really it is. And so now we can obviously start stating facts like vertices are adjacent, and so either they are always adjacent or they are not. And so E is a temporal landscape that tells us the adjacency relation over time. Obviously, this will be always true or always false. And you can ask other questions like, is a agent at position B, between two walls? Does a cell contain a wall, or is it adjacent to a wall, and things like that. So just this to emphasize that, at this level, things are, not very complex. And so moving towards this idea of being intuitive, definitely this really helps, and you can draw things corresponding to these predicates. Now, one thing that one needs to remember, though, is that the underlying logic is not Boolean, but is intuitionistic, which does have some obviously differences. And so here we'll see an example that really sort of exemplify what that means. But it's very useful from a practical application. So if we consider a predicate about occupancy, saying that a certain vertex of my graph or my grid is occupied, then really the temporal landscape, all it tells us is when a certain cell is occupied over time. And of course, you can take the negation of occupied, that obviously we would call the notion of being free. But then one could consider the double negation of occupancy, assuming or thinking that this may actually be just the occupancy, but because the logic is constructed, this does not need to hold. So from a practical perspective, someone that is supposed to use this obviously seems to be particularly annoying, and maybe not even very useful. However, it does capture some subtle nuances that are interesting from an application perspective, and they are very easy to see from the temporal landscape. So as an example, consider three agents, A, B, and C, that occupy cells in the grid world. We can obviously build the temporal landscape for the occupancy of the agent A, B, and C, which tells us which, given a cell, if they occupy that cell or not, and when over time. So we have the temporal landscape for each of them. Say that we want to define the occupancy to really be a predicate describing the intervals over which at least one of the agents is in a cell. So this English sentence has a slightly ambiguity, and this is actually really nicely captured by the occupancy predicate and the double negation of the occupancy. So if we take occupancy to be just the disjunction of the three predicate corresponding to the three agent, the occupancy of B really all it tells us is that, what it tells us is that it is the time intervals when a single agent, either A, B, or C, remain in the cell throughout that time interval. Whereas the double negation of occupancy specifies the time interval over which there is always at least one agent B, and they are allowed to come and go. So in some sense, occupancy keeps track of the identity, whereas double negation of occupancy forgets. So if we move the example one step forward and consider, for example, that the agent A is in a certain cell B over the time interval 0 to 3, B is between 2 and 4, and C 5 and 6, the temporal landscape for occupancy is this. So we see that A is in the cell from 0 to 3, B to 2, 4, and 5 and 6 for C. If you take the negation of this, is a roof whenever this is false, which gives this. And if we take the negation of this, is again the roof whenever it's false, which gives this. And it obviously, if you compare these temporal landscapes, the occupancy and the double negation of occupancy are definitely not the same temporal landscape. So in particular, if you consider, for example, the point 1.5, 3.5, really in the left-hand side, we would say that the predicate is falsified, whereas it's true in the right-hand side. So what is happening here is really that that nuance that I mentioned before, this ambiguity in the statement is really captured by this landscape. And one would wonder, this is interesting. Why would this be useful? How would I use this in practice? Is it meaningful at all? So as an example, think about that there is a light bulb that switches on and blinks, and 2 consecutive blinks correspond to imminent danger. And what you would like to be able to capture is, will it be possible for the agent to recognize that there is danger or not? And so really, so you have this things that blinks, and really the occupancy of B captured the fact that, in reality, A is the only one who is going to be able to observe the fact that the light has blinked in the interval between 0 and 3, so at 1.5, and B will be the only agent able to see at 3.5. But neither one of the two will see it at the same time, during the same, they will not be in the cell when that happens. So unless A and B communicate, there is no way for the agents to know that the danger is imminent. So this is really, again, to simplify, the occupancy of B really sort of keep tracks of the identity of the agents, whereas the double negation of occupancy is sort of a weaker notion. We're only interested to know if there is an agent. We don't keep track of the identity. So this is some complexity that comes from the fact that the underlying logic is intuitionistic, but has very nice interpretations from an application point of view. And the temporal landscapes really shows this very directly. And this example is just showing this.
I just want to give a 5-minute warning.
Perfect, thanks. Now, so far we have been speaking about discrete. You can, of course, extend everything into continuous. So here is another example where we still have an agent, but instead of being on a grid, is moving on a continuous trajectory. And so now this this x, calligraphic x, is all the trajectories that are time parameterized that an agent could potentially follow. And you can start defining position of an agent to be points on this trajectory that are close enough with each other, meaning that the agent has a non-trivial footprint, and that is free, and you assume that the velocity of the agent is bounded. And with this information, you can start asking question of when a certain agent is in a certain room, and you can see more details in the paper, but ultimately you get landscapes that start looking like this, where you can actually associate to every temporal or to every roof the actual room. So the color here is the correspondence. So it's sort of augmented the temporal landscape with some metadata, if you want, on top of it, which is keeping track of the room. And this sort of overlap between proofs really captured the fact that the agent has non-zero footprint, which means that when it's at the boundary, it will be in two rooms at the same time. As a very last example is this idea of our temporal landscape always roof? Can they be something that is different? This example is an agent that is moving in a corridor. It has a LiDAR, so something that spins and provide distance point, the distance to the point that is hitting. And so you can see there are many here and become sparser there. And you may want to track or ask the question, are the samples, these blue dots in memory? And if you have finite memory, when these points are too many, you need to overwrite the previous one, which means that you're going to lose some of those. And so in this case, the temporal landscape actually tends to look like a more curvy one, if you will, where in the beginning we'll saturate the memory very quickly because there are too many points. But and so if we ask if the old point is in the buffer, we'll say no, it isn't. And so landscape saturates. But as we move into sparser area, we can ask, if a certain sample, so a sample persists in memory for longer and longer until we go back to a dense and we'll saturate again. So with this, just capturing the idea here is that while temporal type theory really allows us to really think about and analyze complex behavior, it's a bit difficult to interpret, and the temporal landscape provides this sort of very simple graphical representation to think about it. And really the paper is sort of bringing some sort of realistic examples that could be useful on how these temporal landscapes could be used in practice. That, I'm done. Thanks.
Alberto, thank you. Since we have a couple of minutes for questions, any questioners out there in person or in the virtual space?
There's one here from Leah.
Yeah, let's do it.
Could you give some visual intuition for the contrapositive? So you showed an example of say like phi implies psi. What would not psi imply not phi look like for that example?
Which example you are talking about?
It was, I think, in the first third of your slides when you first showed implication. And you also showed negation after that. I was curious what the interaction of those two would look like.
The interaction. Yeah, I think it's possible. I don't know if I have an answer of what it looks like on the spot, to be honest. But so you're talking about this one, right? The interaction between the implication and the negation.
Yes, the contrapositive.
Right. Yeah, I don't know if I have it's obviously possible. I don't know if I can draw it on the spot. So, but I'm happy to connect. Maybe I don't know if you, David, have an answer for this.
Thank you.
Any other questions in person? Oh, I do see one on chat. Matt Insel.
Yes, thank you for an interesting talk. I would like to know if you've looked at relations between what you've done and classical temporal logic and applications to fault tolerant design, fault tolerance for distributed systems. Thank you.
Yep. Yeah. So the temporal type theory that there is the book by Patrick and have that somewhere here the reference. So this one, the linear temporal logic, metric interval temporal logic, and so on are all embeddable into the temporal type theory. So you can actually represent those using the temporal landscape, I believe, since they are just embeddable. I think what is nice about temporal type theory is sort of that brings all this different temporal logic that has been developed over the years into sort of what we call a big tent of theoretical foundations for thinking about temporal properties. The idea of trying to apply them to fault tolerance system, that's really my interest coming from industry. But to arrive to a point where we can analyze large system, we need a little bit more tools, computer tools that we can use. Of course, there is problem of decidability with temporal type theory, which requires then theorem provers and things like that. But I think I'm absolutely a believer that this is actually possible and should be explored further.
Thank you very much.
Yeah,
Okay.
I had missed some of your talk, so apparently I missed that part. Thank you.
Great. So that's all the time we have in this section. So let's thank Alberto again. And everyone go enjoy a nice, relaxing tea break. We'll see you in the next section.
Can you leave open the chat, the Zoom, so that we can